Hi everyone, welcome back to Chem Story. Today we're diving into another important reaction of alkenes. This time, we're looking at what happens when they react with hydrogen halides. This reaction is called hydrohalogenation, and it's one of the most fundamental electrophilic addition reactions you'll come across. In this lesson, we'll break down how HX adds across a double bond, walk through the mechanism step by step, and talk about what happens in terms of regioselectivity and stereochemistry. Let's start with the basics. Hydrohalogenation is a reaction where a hydrogen halide, like HBr or HCl, adds across a carbon-carbon double bond. It goes through a carbocation intermediate, and it follows Markovnikov's rule. That means the hydrogen adds to the less substituted carbon, while the halogen, like Br or Cl, ends up on the more substituted one. We'll talk more about why that happens in just a bit. Also, keep in mind, this reaction isn't stereoselective. Since the halide can attack the carbocation from either side, you can get both syn and anti-addition. Now let's break down the mechanism. Step 1 is all about protonation. The pi electrons in the alkene go after the hydrogen in HX. That creates a new CH bond. And at the same time, a carbocation forms on the other carbon, the one that was originally part of the double bond. This step is slow, and it's the rate-determining step of the reaction. And here's why it matters. The position of that carbocation decides where the halogen will go, which means it determines the regiochemistry of the final product. In step 2, the halide ion, that's your X-, steps in. This negatively charged ion is now free to attack the positively charged carbocation. It targets the empty p orbital on that carbocation carbon, and when it lands, it forms a brand new CX bond. And just like that, you've got your final product. The hydrogen and halogen have added across the double bond, and the reaction is complete. Now let's talk about regiospecificity, meaning where each atom adds during the reaction. And the key here is all about carbocation stability. The reaction forms a carbocation in the first step, and it always prefers the more stable one. That's why the hydrogen ends up adding to the less substituted carbon, because that leaves the more substituted carbon to carry the positive charge, which gives the more stable intermediate. So whenever you're trying to figure out which atom goes where, just ask yourself, which carbocation would be more stable? That's the path the reaction will follow. Let's look at an example that shows how this actually works. We're adding HBr to an alkene, and at first, it might look like there are two possible products. But if we follow the reaction pathway, we see that it forms the more stable tertiary carbocation. So again, this is a textbook case of Markovnikov's rule in action. The whole point is, the reaction takes the path that forms the more stable intermediate. And here's the energetic explanation for that. If you compare the two possible pathways, one that forms a tertiary carbocation and one that gives a secondary, you'll notice a clear difference in activation energy. The path that forms the tertiary carbocation has a lower energy barrier, so the reaction goes faster along that route. That's why the more substituted product is favored, not just because the carbocation is more stable, but because the entire pathway is more kinetically accessible. Now let's shift gears and talk about stereoselectivity. There are two important things to keep in mind. First, alkenes are sp2 hybridized, which means the double-bonded carbons are flat with a trigonal planar geometry. So when a reagent comes in, it can approach from the top or from the bottom, and both are equally likely. Second, if your starting molecule is achiral, then your product will either stay achiral, or if chirality is introduced, you'll get a racemic mixture. That means you'll form both enantiomers in equal amounts. So bottom line, even though this reaction is regiospecific, it's not stereoselective. So let's go a bit deeper into why this reaction isn't stereoselective. In step 1, the hydrogen halide, HX, approaches the alkene, and because the double bond is flat and planar, it can come in from either side. Then in step 2, the halide ion, X-, attacks the carbocation. And since the carbocation is also planar, the attack can happen from either face of the empty p orbital. So in both steps, there's no preference for top or bottom. And that's why the reaction gives a mixture of stereoisomers. There's simply no control over which one gets formed. This diagram makes it even clearer. Let's say the alkene reacts with H.06, and depending on which face the hydrogen comes from, you get two different carbocation intermediates. Now, from each of those intermediates, the halide ion, X-, can also attack from either the top or the bottom face. And that means you end up with 4 different stereoisomeric products, just based on how the H and X add relative to each other. Some will be syn, others anti, and the molecules might even be enantiomers if a chiral center forms. So once again, because both the protonation and the nucleophilic attack are non-selective, you get a mix of stereoisomers. That's what it looks like when a reaction has no stereoselectivity. So what does that mean for the final product? Well, the added H and X can both end up on the same side of the original double bond. That gives us what's called a syn addition product. Or they might land on opposite sides, and that gives us an anti-addition product. And here's the key takeaway. In most cases, you get both. Here's a nice summary of what we just saw. These 4-box structures represent the different stereoisomers that can form in this reaction. The orange boxes show syn addition. That's when the hydrogen and halogen end up on the same side of the double bond. The green boxes show anti-addition. That's when they're on opposite sides. There's no selectivity, no preference for one outcome over the others. Let's look at a real example to tie this all together. Here, we've got an unsymmetrical alkene reacting with hydrogen chloride, HCl. As the pi bond breaks, the hydrogen adds to one carbon, and the chlorine adds to the other. And here's the important part. The product now has a new chiral center. So we're not just getting one compound. We're forming a pair of enantiomers. One is the R isomer, and the other is the S isomer. And since there's no stereoselectivity in the mechanism, both enantiomers form in equal amounts. That gives us a racemic mixture. So how do we end up with both enantiomers? Well, remember, the alkene is planar. That means HCl can approach from either the top face or the bottom face. And here's the key. The carbon that gets the hydrogen doesn't become a chiral center. So it doesn't matter which side the hydrogen adds from, you still end up with the same carbocation intermediate. That carbocation is flat, and because it's planar, Cl- can attack from either face just as easily. This gives us 2 different 3-dimensional arrangements, and they're mirror images of each other. In other words, they're enantiomers. So even though the reaction isn't stereoselective, the stereochemical outcome still does matter. What you get is a racemic mixture, equal amounts of 2 enantiomers that are both optically active, but together, they cancel each other out. All right, before we wrap up, let's do a quick recap of the key points. First, this reaction is exothermic. It gives off energy as it goes. Second, it happens in 2 main steps, with a carbocation intermediate right in the middle. And the first step, where the pi bond attacks the hydrogen, that's the rate-determining step. It's the slowest, and it sets the pace for the whole reaction. Now here's the important part. The more stable the carbocation, the lower the activation energy, and the faster the reaction. That's why the reaction usually follows Markovnikov's rule, because forming the more stable intermediate leads to a smoother and more favorable pathway. And one last thing, not all hydrogen halides react the same. HF is the least reactive, while HI reacts the fastest. Before we finish, there's one more concept we need to talk about: carbocation rearrangements. These happen when the first carbocation that forms can shift into a more stable one. And since stability drives reactivity, the molecule will often rearrange itself if it leads to a lower energy intermediate. Now, there are a few common types of rearrangements you should be familiar with. One is the hydride shift. That's when a hydrogen atom, along with its bonding electrons, moves over to the carbocation. Another is the alkyl shift, where a whole alkyl group moves instead. And sometimes you'll even see a shift that comes with ring expansion, where the molecule actually opens up a small ring to relieve strain and make the carbocation more stable. These kinds of rearrangements can completely change what the final product looks like, so always keep an eye out whenever a carbocation is involved. Thanks for tuning in, and as always, I'll see you in the next Chem Story video.